Good day to everyone. This is part 2 of the lecture series for embedded system. Today I'm going to show you guys about the general purpose registers that are in our ARM. So ARM, uh, CPU, as we discussed in the previous video, has total of 15 registers. There is R0 to R15 as shown in this figure. And from R0 to R12, they are known as general purpose registers, whereas R13, R14, and R15 are stack pointer, using register, and program counters respectively. So stack pointers, when the programmer does some kind of programming, that is used to store the first address of the stack whenever in use. We'll come to see those in the coming videos in the near future. The link register is used to link one part of code to another part of code, like for functions in C or Java, right? To give a function call. In those kind of situations, link registers are used. And program counters are used to store the address where the next instruction is there to be executed. It does not hold the next instruction to be executed, it holds the address where the next instruction is. Okay, please be very clear about this. Yeah. So the programming model, let's see how it is. Figure 2.2.1, I'll show you the figure in the next slide. It shows the programming model of ARM processor. The ARM processor has a total of 37 registers. All registers are 32-bit wide. Please do not forget this. All registers are 32-bit wide. They can be classified into two groups. There is general purpose registers and special purpose registers. Register R0 to R12 are used as general purpose registers. Depending upon the context, registers R13 to R15 can also be used as general purpose registers. It depends, not in all situations. General purpose registers hold either data or an address, right? Register R13 to R15 um, are there. And then there is a register called CPSR and SPSR. CPSR is a very, very important prospect of embedded system. Everything depends upon it. SPSR, on the other hand, likewise. And all of them included are called special purpose registers. So let's see. As this figure shows, first, this on the top of each diagram, there is a mode written. These are the processor modes, in which mode the processor is going to work, right? So there is actually a total of 6 modes, or in broad category, you can also say 7 modes. First mode or first 2 modes are called user and system mode, which utilizes all the 16 registers. Then there is fast interrupt request mode, which utilizes R8 to R14. Then there is interrupt request where it utilizes only R13 and 14. Same goes for supervisor, undefined, and abort modes. So total 6, right? And the CPSR is there in the user and system mode itself. So the details of these registers, how they function and what they do, we'll see, okay, in this slide. All ARM instructions are 4 byte long, right, as you know, and are always aligned on a word boundary, right? This means that the bottom 2 bits of the program counter are always 0, okay? And therefore the PC contains, or the program counter contains, only 30 non-constant bits, right? So it can often be used in place of one of the general purpose register, R0 to R14, and is therefore considered one of the general purpose registers. However, there are also many instruction-specific restriction or special cases about its use. Usually the instruction is unpredictable if R15 is used in a manner that breaks this restriction. So R15 cannot be used for all the purpose. You can, but it makes it very unpredictable. So better not to touch it. And these are the banked registers. R0 to R7 are for banked. R0 to R7 are banked. This means that each of them refer to the same 32-bit physical register in all processor modes. So R0 to R7 are unbanked registers in all processor modes, right? If you go back, sorry, I can't seem to go back. Anyways, you can go back in your video and see that register R0 to R7, they fall in the category of general purpose registers, but are called unbanked registers because they can be used in the same way for all processor modes. So they are completely general purpose registers with no special use implied by the architecture. and can be used whenever an instruction allows a general purpose register to be specified, right? Okay. Let's clear this up. Register R8 to R14 are called bank register. Why? The physical register referred to by each of them depends on the current processor mode. See, physically, actually, there are the 16 registers only, but in different modes, they have different actions. So as we saw in the video, those were the different modes, but physically, there are 16 registers only. Okay, in different modes, they have different functionalities. In different modes, they can be used differently. Okay, so let's see. Where a particular physical register is intended without depending on the current processor mode. More specific name is used. All the instructions allow the bank registers to be used wherever a general purpose register is allowed. Right? So out of 37 registers, 20 registers which are shown in shaded are the bank registers. Right? Also shows figure 2.2.1 also shows which bank registers are used in which mode. Bank registers of a particular mode are denoted by R, then the number underscore the mode, right? We have seen this in the diagram. So as for example, supervisor mode has bank register, so R13 underscore SVC. SVC is for supervisor, right? R14 underscore SVC, SPSR underscore SVC, and all that. On the other hand, abort mode again has the same, uh, nomenclature R13, uh, but underscore ABT and all that. Right. Register R8 to R12 have two bank physical registers each, right? The first group of physical registers are referred to as R8 underscore user, R12 underscore user, and the second group is R8 underscore FIQ and R12 to R12 underscore FIQ. So the R8 underscore user to R12 underscore user group is used in all processor modes other than FIQ. Yes, we have seen this, right? And these others are used in FIQ mode. Our registers R13 and 14 have six banked physical registers each. One is used in usual system mode, while each of the remaining five is used in one of the five exception modes. Right? Okay. Right. So let me be clear. R0 to R15 are the different registers. Then it has a CPSR, and there are a total of six modes. In whichever mode they can be utilized, they are shaded ones are banked, unshaded ones are unbanked. Right? Okay. Let's see this. This is just an introduction to different kinds of instructions and their descriptions that are used in ARM assembly language. Okay, these are the instructions that we are going to see in the coming videos, where you have how you want to manipulate your program based on your needs. You want to add, you want to compare, you want to XOR, you want to or you want to subtract, reverse subtract, all these things. We'll see this clearly in the coming videos of Module 2. Let's see the addressing modes. First, let's see addressing without offset. Here, if you see the instruction, it's written as LDR R1, comma, inside third brackets R0. So what happens here is whatever address or whatever content is there in R0. Now R0 is a register in the ARM CPU. Now it will go to the peripheral memory, right? It will check there for it will check that address which R0 holds. So R0 will have some kind of address. In the control will go to that address and copy the contents of that address to R1. So don't be confused. The contents of R0 does not get transferred to R1. Here, the address that is stored in R0, in that address, whatever is there, that comes to R1, right? So R0 will hold the memory address, right? Okay, and let's be clear about this through some examples, right? Let's see. State the contents of R2, R1 and memory location 0x20 after the following program, right? Okay, first comes MOV. MOV is for move. If you write MOV R2 hash 0x5, what will happen is hexadecimal 5 will enter into R2. Okay, please be clear about it. Hexadecimal 5 in the first line of the program, hexadecimal 5 will enter into uh, this R2, right? Then MOV R1 0x2, same hexadecimal 2 will enter into R1. Then add R2 comma R1 comma R2. What will this do is it will add or it will do R2 equals to R1 plus R2, right? So the sum 7 will be stored in R2. Yes. Then again add R2 R1 R2. Again R2 equals to R1 plus R2. So the R1 was 5 and R2 became 7 in the previous statement. So 7 plus 2 becomes 9 and 9 will enter into R2. Then MOV R5 hash 0x20. Yes, so 0x20 will enter into R5. Then you write strb. Strb is short for store byte. Okay, it will store one byte, right, from R2 to the address pointed by R5. Now in R5 there is 0x20. 0x20 is a memory location in the main memory. So whatever is the content in R2 or register 2 will be transferred to the address location 0x20. Okay, it will not replace 0x20, but in the 0x20 location, 9 or hexadecimal line will be stored, right? So this clearly shows how what I said occurs. I hope this clarifies it for each. So let's see one by one. So in first, in location R2, 5 enters, then in R1, 2 enters, then 5 plus 2 becomes 7 and it enters into R2. Then 7 plus 2 occurs and it enters into R2. And till now 0x20 is not loaded, right? 0x20 is assigned to R5 and we load the value of R2 into the contents pointed by R5. So the contents pointed by R5 is 0x20. So in that 9 is transferred. So I hope this is clear. Next, let's see another example. State the contents of RAM location 0x92 to 0x96 after the following program is executed, right? Okay, see this program, it's a little lengthy, but it's quite simple if you go through it. Okay, I have given the solution right away. Please check this. Move R1 hash 0x99. So hexadecimal 99 will enter into R1. Whenever 0x is there in front of a number, that means it's a hexadecimal number. So 99 will enter into R1. Move, the next statement is move R6 hash 0x92. So 92 will enter into R6. This is hexadecimal 92. Then again, strb R1 comma R6. So what happens here is the contents of R1 are transferred to the location pointed by R6. So the location pointed by R6 right now is 92. So R1 is 99. So 99 will enter into the location 92. Right? Okay. I hope it's clear. Then add R6 hash 1. That is add R6 equals to R6 plus 1. That becomes what? 99. Sorry, R6 was 92. So now it becomes 93. Move R1 comma hash 0x85. That is hexadecimal 85 will enter into R1. And store B R1 R6. So R1 will enter into the location pointed by R6. Location pointed by R6 right now is I think 93. Yes, so 85 will enter into 93. Right. Again, add R6 equal to R6 plus 1. R6 is incremented by 1. So now R6 becomes 94. Move R1 0 3F. So 3F will enter into R1. strb R1 comma R6. So R1 will enter into location pointed by R6. That is 3F will enter into 94. Okay. Then again add R6 hash 1, that is R6 will be incremented by 1. Now it becomes 95. Move R1 63, so R1 becomes 63, strb R1 R6, where R1, that is 6, which has value 63, will enter into location pointed by R6, that is in location number 95. Again the same procedure, add R6 R61, so now R6 becomes 96. So let's go to, then again move R1 comma 0x12. So 12 will enter into R1, strb R1 R6, 12 will enter into location pointed by R6, that is in 96. So clearly the answers are written on the right hand side of this slide. I hope this is clear to you. If you have any doubts, please write in the comments. I'll try to clarify it. Okay, that's all for today. Thank you for watching this video. Please like and subscribe. And if you have any doubts, please do not be hesitant to comment. Thank you.